my previous video I had seen reducibility and irreducibility test. Today I will see some more test with more example. Actually this topic is very important for higher study, also for any competitive exam. At first see what is the Eisentien's criteria. We all of us know Eisentien's criteria. In my previous video I had seen. Just as a review, if fx is a0 a1x plus a2x square up to nx to the power n g belongs to zx, then fx is irreducible over q if there exists a prime p such that p divide a0, p divide a1 up to p divide an minus 1 and p does not divide an and p square does not divide a0, then we can tell fx is irreducible over q. And we all of us know if GCD of means function is monic polynomial, GCD of a0 up to an equal to 1, if the coefficient is 1, then fx is irreducible over z also. Here I will see one new topic. Fx belongs to fx and AB one member of field. Then if f of ax is irreducible, that implies f of x is irreducible over f. Similarly, a times fx is irreducible, then we can conclude fx is irreducible over f. Similarly, f of x plus a if irreducible, then that implies fx is irreducible over the field. Let's see some example, then this part would be more clear. What is the cyclotomic polynomial? If fx equal to 1 plus x square plus x cube up to x to the power p minus 1, where p is a prime number, then we can tell fx is irreducible over q. And since GCD, the function is monic polynomial, so fx is also irreducible over z also. Let's see one question which had come June 2015 exam, CSIR NET exam. The question is, which of the following polynomial are irreducible in the ring zx of the polynomial in one variable with integer coefficient? Option A, x square minus 5. Option B, 1 plus x plus 1 plus x plus 1 whole square plus x plus 1 whole cube plus x plus 1 to the power 4. Option C, 1 plus x square plus x cube plus x to the power 4. Option D, 1 plus x square plus x cube. Which of the following polynomial are irreducible in zx? Fx equal to 1 times x square plus 0 times x minus 1 times 5. Notice by Einstein criteria we can tell here p equal to 5. Then p divide here 5 divide minus 5. Here an means second degree polynomial, so the coefficient is 1. 5 does not divide 1. Also here a0 means minus 5. 25 means p square does not divide minus 5. So for p equal to 5, Einstein criteria is satisfied. So this polynomial is irreducible polynomial. So option A is the right option. And notice option B, 1 plus x plus 1 plus x plus 1 whole square plus x plus 1 whole cube plus x plus 1 whole to the power 4. At first think also. This is which type of polynomial? Is here fx equal to 1 plus x plus 1 plus x plus 1 whole square plus x plus 1 whole cube plus x plus 1 to the power 4. If we define new function gx equal to f of x minus 1, then this would be 1 plus x minus 1 plus 1 plus x minus 1 plus 1 whole square plus x minus 1 plus 1 whole cube plus x minus 1 plus 1 to the power 4. Next, gx equal to 1 plus x square plus x cube plus x to the power 4. Notice gx is irreducible polynomial because here 1 plus, this is the cyclotomic polynomial, 1 plus x squared up to x to the power p minus 1, this is the cyclotomic polynomial, and this is irreducible if p is prime number. Since here p equal to 5, so 5 is since prime number, so this polynomial gx is irreducible. Gx is irreducible over q. Since gx equal to f of x minus 1, so fx is also irreducible over q by this property. If f of x plus a is irreducible, then we can tell f of x is irreducible over f. So here fx is irreducible over the q, and since this polynomial is cyclotomic polynomial, so this is also irreducible over z. So option B also right option. Notice option 3. Here 1 plus x square plus x to the power 4. This is just cyclotomic polynomial. Here p equal to 5. Here not, here f of x plus 1, or this is just cyclotomic polynomial, this polynomial. So this is irreducible over q, also over z. Here notice, here cyclotomic polynomial, this is right, but here p equal to 4, this is not prime number. So since cyclotomic polynomial is irreducible over q when the p equal to prime number, but here since p is not prime, so option D is not right option. Only option A, option B and option C is the right option. Next result is mod p test. Let p be a prime and suppose that fx belongs to zx and degree of fx greater than equal to 1. Let f bar x, which be the polynomial in zpx, which obtained from fx by reducing all coefficient of fx in modulo p. If f bar x is irreducible over zp and degree of f bar x, if degree of f bar x, which is reducing polynomial over zp, whose coefficient is reducing by modulo p, then if f bar x is irreducible over zp and degree of f bar x is equal to degree of fx, then fx is irreducible over q. That means if a polynomial fx is reducing over mod zp, then the new polynomial, reducing polynomial is f bar x, whose all coefficient reducing by modulo p. If degree of f bar x is equal to degree of fx, where f bar x is the reducing polynomial over zp, then this reducing polynomial f bar x, if f bar x is irreducible over Zp, then we can conclude this fx is irreducible over Q. But if f bar x is not irreducible over Zp, then we cannot conclude anything about fx. For this, consider x cube plus x square plus 1. Is it irreducible over zx? Consider the polynomial p equal prime p equal to 2, and f bar x, which is reducing over the field Zp. By reducing, this polynomial would be x cube plus x square plus 1. And notice, degree of f bar x is equal to degree of fx. Okay? And in Zp, here Zp is Z2. In Z2, f0 is not equal to 0. Also, f of 1 is not equal to 0. So, in Z2, since f bar x is irreducible, so we can tell fx is irreducible over Q. And since the polynomial is monic polynomial, so fx is also irreducible over Z. Okay? But if you consider p equal to 3, then notice f of 1 would be 1 plus 1 plus 1, which is equal to 3, and which is congruent to 0 in mod 3. That means in Z3, the polynomial is reducible polynomial. But see, we cannot conclude anything about reducibility or irreducibility of this polynomial. When any prime this f bar is reducible, then we cannot conclude anything about this polynomial. When we can able to find any polynomial p for which f bar is irreducible, then we can tell fx is irreducible. But for any prime we can tell f bar is reducible, then we cannot tell about fx anything. Determine which of the following polynomial are irreducible over the field f. Option 1, x to the power 5 minus 3x to the power 4 plus 2x cube minus 5x plus 8 over R. Is it polynomial is irreducible or reducible? We all of us know, in real field, when n is odd, then over R it has always at least one root. Since here 5 is odd number, then at least one root alpha I will get. So since alpha is a root, at least one root, so x minus alpha is a factor of this polynomial always. So this is the reducible polynomial. So option 1 is a wrong option. Option 2, x cube plus 2x square plus x minus 1 over Q, is it polynomial is irreducible? For this, here I will use the mod p test, mod p irreducibility test. Fx equal to x cube plus 2x square plus x minus 1. If we consider p equal to 3, then over Z3, 0 bar, 1 bar, 2 bar. And over Z3, the polynomial reduces, f bar x would be x cube plus 2x square plus x minus 1. And notice here f bar 0 is equal to 1, which is not equal to 0 in modulo 3. F bar 1 1 bar is equal to 5, which is congruent to 2 in modulo 3, and f bar 2 bar class of 2 is equal to 8 plus 8 plus 2 plus 1. This is equal to 19, and 19 in modulo 3, this value would be 1. This is also not equal to 0 in modulo 3. So this polynomial f bar x is irreducible over Z3. Since degree of f bar x and degree of fx is same, so degree of f bar x and degree of fx is same, so we can tell this fx is irreducible over q. So option 2 is a right option. Option 3, here I will x cube plus 3x square minus 6x plus 3 over z. Here also I will use Eisentien criteria. Consider p equal to 3, and notice n equal to 1, 3 does not divide 1, but 3 does divide n minus 1. Here 3 divide 3 divide minus 6, 3 divide 3, a not equal, but 3 square means 9 does not divide 3. So by Eisentien criteria we can tell this is irreducible over q, and since this polynomial is monic polynomial, so this is irreducible over z also. X to the power 4 plus x square plus 1 over z2, we have to find is this polynomial is reducible or irreducible. Is z mod 2z means here class of 0 and class of 1, and f0 equal to 1, which is not equal to 0 in mod 2, and f of 1 equal to 3, which is also not equal to 0 in mod 2, but we cannot conclude about fx because degree of fx is equal to 4. Mod p test only applicable when degree is either 2 or 3, otherwise it cannot be applicable. Since degree here 4 greater than 3, so by this mod p test we can tell there exists no root, but we cannot any conclusion about fx. Notice for this, for factor over z2, degree 1 polynomial is x plus 0, 0x plus 1. Here x to the power 4 plus x square plus 1. At x, for x cube this would be x to the power 4 minus x to the power 4, then x square plus 1 plus x, this would be x square, then this would be cancelled, then this value is 1, and this is not equal to 0 in mod 2. Now check for degree 2 polynomial over z2. What would be the factor of degree 2 polynomial over z2? This is x square plus x plus 1, and x square plus x plus 1, here x to the power 4 plus x square plus 1, this value would be x square, this value would be x to the power 4 plus x cube plus x square, then this value minus x cube sorry, here x to the power 4 plus x square minus x cube, here this would be cancelled, plus 1, here minus x, then this value would be minus x cube minus x square minus x, then this value would be x square plus x plus 1, here plus 1, then this value is x square plus x plus 1, this is 0. Therefore, we can write x square plus, we can write x to the power 4 plus x square plus 1 as x square plus x plus 1 times x square minus x plus 1. X square plus x plus 1 is a factor of this polynomial. So, fx is not irreducible over Z2. Here I have done one printing mistake. Here over Z2, not Z3. Here in over Z2, degree 1 polynomial is this, and over Z2, degree 2 polynomial is this, x square plus x plus 1. This polynomial is reducible over Z2. So option 2 and 3 only right option. Today I will stop here. In my next video I will discuss reducibility of irreducible polynomial with elaborately with some example which had come different type of competitive exam, because this topic is very important for higher study. Okay, see you soon, stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.